Let's start. Yeah, hello everybody. Welcome to the first early career session this semester. We will have another early career session on December 16. Yeah, so today we will have a tight schedule, so there may not be time for questions after each talk. Some of us, yeah, whoever wants to stay afterwards is welcome to stay. Then there'll be more time for questions. And let's get right to it. Our first talk is by Peter Sarnak, who will speak about minuscule, posets, and superpotentials for cominuscule homogeneous spaces. Please go ahead.
Peter Spacek.
Peter Spacek, did I say it wrong?
That's all right. Let's just get started because we're on a tight schedule. Right, so I'm introducing some recent results from mine and Charles Wan's that we posted to archive 2 months ago, maybe a month and a bit. So we're talking about minuscule posets and superpotentials for something called a cominuscule homogeneous space. So I'll introduce quickly these concepts and what kind of results we got for them. So superpotentials makes you think of mirror symmetry, and indeed we're talking about mirror symmetry, namely for the small quantum cohomology. Now I was told to keep this as general as possible, so I'll give you a very vague introduction to the small quantum cohomology. And in vague words, this is an extension of the ordinary cohomology where we count intersecting curves instead of intersecting points. So this is an extension because, of course, the degree 0 curve is just a point. So we sort of extend the original idea. And to have like a baby example of a small quantum cohomology, let's look at the cohomology of the projective plane. I hope everybody knows that this is isomorphic to a polynomial ring over the hyperplane class or a line class. And that if you take 3 lines, then you get the 0 intersection points. And this is a nice thing to look at because it tells us, well, 2 lines intersect in a unique point. What this, however, cannot tell us is that if you take 2 points, then there's a unique intersecting line. And this is what the small quantum cohomology is perfect for. This is exactly describing this property in this equation, saying that this quantum product of a point and another point is 1 line. So in this case, we find that the small quantum cohomology is a polynomial ring over 2 variables, this hyperplane class or line class, and the quantum parameter, which is telling us how quantum things are. And we find that this relation is now not that 3 lines have 0 intersection, but have q intersection. This is still a bit vague, I guess, so I'm going to argue a bit how this small quantum product is defined. So let's look at the intersection product of 2 lines. Well, in the normal cohomology, this is telling us that a line and a line is 1 point. And here I've written the number 1 in a very strange way, namely as the number of points in the intersection of a generic line with another generic line and the whole space. So why is this whole space interesting? Well, a point is Poincare dual to the fundamental class. And that is why we now see this whole space showing up in both the count and in the product. So the idea is now to change this intersection product instead to a sum over all over the whole basis of the cohomology. And you just take a basis, you look at the number of intersection points of these three varieties we're looking at and the Poincare dual. And then this is where we switch to the small quantum cohomology. We're now not only looking at intersecting points, but intersecting curves. So you sum over all the degrees that your curves can have, and then you sum over a basis for your cohomology. You look at the degree d curves that there, which is the number of them that intersect these 3 varieties, and then you take a Poincare dual and add a formal parameter q with a d that keeps track of what kind of degree you're looking at. So these triples are called Gromov-Witten invariants. They're pretty hard to define. You need virtual fundamental classes and and other problems arise when you don't have nice spaces. And even this notation is not really the most general notation, but still a special case that Picard rank is 1. Namely, there's only a single line, single degree 1 curve. And if you have more degree 1 curves, then you have to add more quantum parameters and things become even more complicated. So what is this telling us? Well, it is very nice to have an expression like this, where the quantum cohomology is written as a polynomial ring with relation. And this is what mirror symmetry is working towards, is finding other expressions in terms of polynomial rings with relations for small quantum cohomology. At least in the field that in the area that I'm working at, there's more global, more kinds of mirror symmetry out there as well. So now we get to superpotentials. In the idea for Plano varieties is that if you have mirror symmetry, then you need to find on the mirror side something that is called the Landau-Ginzburg model. It is a pair of a variety and a regular function on this variety depending on this quantum parameter, such that if you take the coordinate ring of X of this variety times the formal parameter space, and you quotient out by the relations generated by the derivatives of your function, then you get back this small quantum cohomology. With as additional allowance that you now also allow this formal parameter to be inverted. And if you find such a pair, then this variety is called the mirror variety, and this regular function is called the superpotential, for reasons coming from string theory, when mirror symmetry was still in its start. Again, this notation is for Picard rank 1, otherwise you have more parameters, and this C star becomes multiple copies of C star, but I guess you can extrapolate. So how does a Landau-Ginzburg model look like? Let me give you another baby example. Consider this function W that goes from C star squared to C, taking these two coordinates, summing them up, and doing plus Q times 1 over A1, A2. So this lives in the coordinate ring of C star cubed, where two of them are the variety, and one of them is parameter space, for the quantum parameter space. So you get the round polynomial ring over 3 variables. And the associated ideal, the Jacobi ideal, as it's also called, is of course this. We can all take derivatives of this such a polynomial, the wrong polynomial. But now if you see, these two generators look very similar. So if you multiply the first one with A1 and we multiply the second one with A2, and you take the difference, then you see that this contains the ideal A1 minus A2, right? So if we take the quotient of this coordinate ring by this Jacobi ideal, then we're just identifying the two coordinates. And what is left is one generator of the form 1 minus Q times 1 over A cubed. And if we now recall how our small quantum cohomology would look like for CP2, well, that is practically the same as long as we allow inverses of Q. And that tells us that this potential gives us a Landau-Ginzburg model for the projective space. So these Landau-Ginzburg models are relatively hard to construct. There's been mostly progress in toric varieties and in what is called homogeneous spaces, also known as flag varieties. So this is the next part of the talk. So what do I mean with a homogeneous space? A homogeneous space is a complex projective variety with a transitive action of a linear algebraic group, or Lie group if you prefer things analytically, and the stabilizing subgroup is called a parabolic subgroup. So there's plenty of examples out there. You can look at flag varieties or isotropic flags if you give C2 to an inner product or symplectic form. But our favorite example of Grassmannians are, of course, homogeneous spaces, but these are actually special homogeneous spaces. They are called cominuscule homogeneous spaces because this parabolic subgroup stabilizes something that is called a cominuscule weight. Now, this can be defined in terms of weight theory, but it's easier to look at the equivalent definition of minuscule weight. But let me mention first a few examples. Other than Grassmannians, you also have spaces that are called orthogonal or Lagrangian Grassmannians, which are maximal isotropic subspaces in C to N with inner products or symplectic forms. So what does this cominuscule weight give us? Well, if you look at what is called the Langlands dual homogeneous space, although this might be our original terminology. So what is this homogeneous space obtained by taking the Langlands dual groups for G and P? So if you've never heard of this, G has a root lattice and a character lattice, and a character lattice and a co-character lattice, and G check is the one that is the unique group that has those two interchanged. So in practice, if you have a group of type A, then the dual will also be a group of type A. If you have a group of type B, then the dual will be a group of type C. And then there is something that happens with the fundamental groups of these, of the group that changes as you switch as well, but that's not so important. And what is nice, that if your original space is cominuscule, then this Langlands dual space is what is called minuscule, which means that it has a natural embedding into a projectivization of a minuscule representation. And this gives you a very natural set of coordinates called Euclid coordinates or generalized Euclid coordinates. And this minuscule representation is also how we get minuscule posets. Let's see, yes, very good. So what is a minuscule poset? Now we get into the proper combinatorics. So let's start with the minuscule representation. So what is a minuscule representation? It's nice in the sense that all of its weights form a single orbit under the Weyl group of the group. So that is telling us every weight space is one-dimensional, and that you can get from every weight space to another weight space by acting with a nice Weyl group element. And for minuscule posets, minuscule representations, we now give these weights the partial order where the difference has to be a positive linear combination. And then in 1984, Proctor showed that this poset of weights forms a finite distributive lattice. So what is this? A lattice is a partially ordered set such that every two elements has a join and a meet. So a smallest element that is bigger than both, and a largest element that is smaller than both. If you have both, if both of those elements exist, then you have a lattice, and then it's called distributive if these two operations of join and meet they distribute over each other. Now, why is this a nice property? Well, earlier, Birkhoff showed in 1937 that if you have a finite distributive lattice and you consider the induced poset of joint irreducible elements, so all elements that cannot be written as the joins of two other elements, then the original lattice is actually isomorphic to the poset of order ideals of the joint irreducible elements. So this allows you to consider the whole poset in terms of smaller poset and an order ideal in there. So it compactifies all the information into a smaller poset, and combining these two things leads us to define what is a minuscule poset, namely one of these posets that can be obtained as a poset of joint irreducible weights of a minuscule representation. All right, so for an example, okay, so firstly, these are very nice posets because it turns out that all of these minuscule posets can be drawn as a skew Young diagram, which is not, so you allow like holes in the rows. So the left side doesn't need to be flushed against the rim of the triangle. I mean, I'll give you some examples and then I hope you will see. So one of these examples is a nice one, I think, is if you look at orthogonal Grassmannian of maximal isotropics subspaces in C12 with the inner product, the normal inner product. And this is a homogeneous space of type D6 with the parabolic subgroup stabilizing the sixth fundamental group weight. And then its Langlands dual will be embedded into the spin representation. So like I said, the weights form a single orbit. So each of these dots represents a one-dimensional weight space. And two weight spaces are connected by an edge with a label I if that simple reflection maps the two weights to each other. And we see that we can label each of these weights by an order ideal of this large staircase Young diagram, namely where each box represents a joint irreducible weight, namely one that has only one other element to its right. So here you get one box because this weight has only one element to its right. Here you get a new box because that one also is a joint irreducible. And then here we have two ways to add a box. And then this guy is not joint irreducible because you just add both boxes there. So you don't get a new box.
15 minutes.
50 minutes, right? So we can take this Minuscule poset, and then we label the boxes by the simple reflection that lowers the weight. So you get this nice labeled Young diagram. So what do we use these Minuscule posets for? Well, this is our main result that we put on arXiv a month ago. Namely that if you take a cominuscule homogeneous space, then there are rank G+1 homogeneous polynomials in these supercoordinates that have a number of properties. Firstly, the zero divisor is an anti-canonical divisor. And actually, they form the frozen variables of a cluster structure on this Langlands dual space. And then secondly, we can define a Landau-Ginzburg model using these homogeneous polynomials, where the mirror variety is the complement of this anti-canonical divisor in this Langlands dual space, and where the potential is given by a sum of quotients with the denominators, these homogeneous polynomials, and the numerators obtained by some kind of derivation applied to this polynomial. And what is nice is that these denominators and numerators are very easily constructed by combinatorial means, and that we have very nice combinatorial around polynomial expressions for them. So what kind of combinatorials? Like I'm foreshadowing, it's the order ideals of Minuscule posets. So to finish off this talk, let's give you a small example of how to construct these polynomials. So going back to OG612, the third of these polynomials is given by this alternating sum. And how do you get this sum? Well, the important information is the 6 that defines the parabolic subgroup and the 3 that defines the third denominator. And then you look at the Dinkin diagram of the Langlands dual, which is still D6. You remove the 6th vertex and you look at the third vertex in the resulting Dinkin diagram. Apply Dinkin involution if there's a result or not. In this case, it doesn't do anything. And this gives you a first number. And then the second number is obtained similarly, but this time we remove the third vertex and we look where the 6th goes to. And in this case, you get an A3, which has a non-trivial Dinkin involution, so 6 get mapped to 5. And what do you do now? We look at the biggest order ideal of our Minuscule poset that you can make without using this 3. And that is this little staircase. The 3 is underneath here, so we cannot go any further. And then we complete it to the biggest order ideal we can make without using another 5. So there was already a 5, that is fine, but we cannot use another 5. And then we get this poset. And then the other terms are now obtained by moving boxes, as allowed by the Minuscule poset. So first we can move the 5, then we can move a 4, then we can move the 6, and that is how we get the alternating sum. And then to get a denumerator, all we do is we take this 3 and we try to add a box with this label to each of these terms. And there's only 2 terms where it's allowed, and only in the smallest polynomial, the smallest order ideals, and it is how we get the numerator. And this works for all the terms except 2 special ones, the quantum term, which is when this 6 is the same as the I of our denominator, then something special happens. And there's an extra term, which is the smallest term, which is called the 0th term. And that is what I wanted to advertise.
Very nice. Thanks very much for a very nice talk to Peter Spacek. And I apologize for messing up the name. Let's thank the